All right, I think today is the day that we should take our toy chemistry program and extend it into another dimension. I've done a little housekeeping to make that transition easier. I've changed the way that my particles are generated so that I can have an arbitrary number of particles. I'm still creating the 0th particle individually because that's the driven particle. That's the one I definitely want marked as white. In fact, let's even distinguish it a little more by making it 20% bigger in radius. That doesn't actually impact any of the physical calculations. That's just its visual representation. I've commented out my manual particle creations here. I don't want to get rid of those just yet, just in case I need to go back and manually create some particles. But what I'm doing right now is I'm going over a loop of this I particle, going from 1 to the number of particles, and we're giving them a random color. We're going to give each one a random RGB code, and we're giving it a random X coordinate between -5 and 5. So this is a uniform probability distribution I had to write into the code because this built-in random function only goes between 0 and 1. This one will go between the lower bound and the upper bound. I'm not going to go over that. I showed how that was made in a VPython for Beginners video that came out recently, so you can go check that out if you're interested. And then, like before, we're adding each of these particles to the list. We're giving it its randomized position and its randomized color. Notice I'm giving these a Y and a Z, so that when I want to extend this to 2 dimensions, all I have to do is change these 2 numbers, and the code will suddenly be in 2 dimensions. I've also had to change the way I loop over the particles because I have an arbitrary number of particles. I'm creating the bonds and arcs list a little bit differently. So each one starts out as an empty list, and then basically as we loop over each particle, we need to add the row for that particle inside these matrices. And so what I've got down here is the bond list and the arc list. So this is a temporary list to store that row of the matrix in. That row or that column? I guess it's that. If it goes row, column, I mean, it ultimately doesn't matter. It's a 2D representation either way. So for J underscore particle in range, blah, blah, blah. So we're going over all the other particles again. And again, we want all of the bonds to start out at 0. So we have unbonded elements at the beginning. And then we are creating here we're creating the arc if we haven't before. So if we've got I less than J, then we're creating the arc. Otherwise, we're not creating it because we don't want to double up on the number of arcs created. And then we just append that list to these lists. So these lists are lists of lists. This is how it was set up before. Again, I've commented it out in case I need to go back to the previous version. Oh, that's a very old line right there, that extrusion. Yeah, that I don't need to have anymore at all, so let's just delete that. All of our constants are going to stay the same as before. We're not worrying about changing those just yet. I would like to, let's add this graph back in. I've removed the graphing down below, but I think I'll add that back in a minute. And so here we're doing the same loop. We're looping over the bonds to get the bonding rates. And then as the particles move, we're also updating the arcs. We're updating the arcs right here. So we're turning the arcs on and off, and I think we set their position. Yeah, we update the arcs position here, so they're technically half a frame behind the particle locations, but that doesn't really matter to the human eye, especially not at 500 frames per second. And then here we've got our usual updates of the velocity and the position. This is looking kind of boring compared to everything else that's going on up in the rest of the program. And then this is where I was graphing the percent time bonded, but I think everything's turning out the same, so I'm not going to worry too much about that. Let's do a Control-2 to run this code. It should look the same as it did before because I've still got 3 particles. The only change is we've got randomized colors on the other 2. They look kind of like gobstoppers or something. And lo and behold, we do see the same type of behavior that we had before. The white one is being driven back and forth along the x-axis, and the other 2 kind of follow behind as they are bonded. It looks like our bonding is sticking around for most of the time like we saw before. Learned a new command today, Control/ will turn comments on or off for multiple lines at a time. Let's double check that graph. Last time we were getting, very high percent time bonded, as we would expect. And lo and behold, that's what we get here. I I don't remember it starting out at 0. Maybe I have it updating a different time now. But yeah, it very quickly gets up close to 100% of the time spent bonded, and it doesn't really drip down that much. I mean, you can see here the bonds are flickering on and off, but they're definitely spending more time on than off, especially since this is a logical OR. So this is if particle 1 is bonded to particle 1, if particle 0 is bonded to particle 1 or particle 2. So that's going to be most of the time by definition, unless it's a really, really small bonding rate. Okay, so I feel comfortable with that, so I'm going to turn that off so that I don't have to worry about that taking too much computer time. Let's have a little fun before we go to 2D. Let's increase our number of particles. I've got that all the way up here. Let's turn that into a 5. And so this will give me 5 particles. So I've got lots more combinations to try out now. And so they quickly fall in close to each other because of that damping force. So I might want to turn down the damping force at some point. And again, you get the same kind of behavior you had before. Let's zoom in here. So the white, the driven particle is pulling the others along back and forth. You fall into that resonant pattern pretty quickly. So let's have some fun now. In our last few minutes, let's get to the actual point of this video and turn this thing into 2 dimensions. So I'm just going to copy this and paste this into the Y direction. Let's not do Z yet. Let's save that for later, especially since I went ahead and named the code Toy Chemistry 2D. Let's have this be X and Y and uniformly distributed between -5 and 5. So these are going to start out in a 10 by 10 square, and here they come. Oh, that was kind of cool. The brown one got connected as soon as it came in closer to the others. So these are still oscillating up and down a little bit, but that's going to tend to die out. Eventually, we're going to get this just in a left-right behavior. So I wonder, I bet I could make that a little more interesting if I were to make the white particle, the particle 0, go around in a circle. So let's actually change a couple things. First thing let's do is decrease the drag coefficient. Let's cut that in half so that we have a little bit more interesting material for a little bit longer time. And then I want to change the way this driving force works. Let's see here. Where do I add in the driving force? Let's see, forces are calculated down here. Well, driving force on particle 0. Okay, let's do this. So, and I do have these in multiple dimensions already, right? I've got particle list net force equals dot position, so that's a vector. Then I've got net force and equals net force plus the damping force gets the velocity. Okay, so that's as a vector. That's good. What about the interparticle forces? Do I have those? The interparticle forces here. I do have those based as vectors. Okay, so I wasn't just working in the x direction. Okay, figured I should probably check that. Okay, let's do the same thing here. So the x was being driven like the sine. Let's change that into a cosine. Because if you want to make something move in a circle, you make the x move like the cosine and y move like the sine. I mean, you could have it the other way. That just changes the direction it rotates in. But usually we give x the cosine and y the sine. So these have the same amplitude and the same frequency. So that white one should be moving in a circle. So we're going to see a few things different. We're going to see less damping force. We're going to see circular motion for the white particle. Oh, now that's cool. Somewhat circular. Oh, that's right. It's being pulled back by the others. So although the driving force is circular, it's still being pulled back by the others. Yeah, it's starting to fall into a little bit more like a circle now. Yeah, but it's being pulled back by the others. So that's kind of cool. Oh, that is neat. It is moving everybody else along nicely. I'm still losing a bit too much energy to that, I feel like. Let us decrease that damping force. I'm almost tempted to turn the damping force off, but I feel like that's going to be a mistake. Let's decrease this by another factor of 5. So this is now 10% of what it was before. Oops, no, not Control F2, Control 2. There we go. This will be our last view for today. Here they come in. I'm not sure why it pauses like that at the beginning. I'm not sure what it's initializing there. Okay, so we get caught up into that pretty quickly. Maybe that's not the damping force causing that. Maybe that's all of their bonds forming. So anyway, that's pretty fun to look at. I'm going to play around with those numbers a little bit, see if we gain any other insights by looking at it in 3D as opposed to 2D. I also want to fix up these bonds to where maybe they go in a straight line now that we're in 2 dimensions, so we don't have these things just kind of sticking off like that. Anyway, that was fun to watch. Thank you so much for joining me. I will see you next time. Bye-bye.